Okay, so last time we started working on a problem which was the spinning beam. So it was a intrinsically 2D problem. We have the dimensions as, well, let me, in a slightly rough manner, sketch the problem once again. That was the beam. So we have two symmetry planes. Okay. Symmetry planes in the sense that eventually I know, for instance, that sigma 1, 1 is the same as sigma 1, 1 there, etc. And which actually was a critical observation for us to frame what the Airy stress function was. We essentially made two important observations. The symmetry of the stress, okay, of the normal stresses, eventually shear comes out to be 0 anyway, and the fact that the stress is not a constant. So it will have a variation, and it's going to be some sort of a symmetric even variation, even function of the coordinates. So only based on those coordinates, we were able to find out what the Airy stress function was. And eventually, the function is, after the discussions that we made, was the following. So it was a quartic function of the coordinates. You don't have to write this part down because it's really just a review of what we did last time. Just listen so we can remember the most important parts. So this was the Airy stress function. So with this Airy stress, this is the most possible polynomial Airy stress function we can propose. It delivers a variation of the stresses. It's not a constant. And that variation is an even function of the coordinates because the stresses come out to be 2 orders less. So they are going to be quadratic. So they're going to be quadratic and constant terms. And eventually we found what these constants were. And in fact, we found out that A2 was identically 0. So this term actually dropped out. And we were left with the expressions for the stresses. So remember that in the original problem, so just one second. I have shuffled my notes around, and now I cannot find page 3. OK, here it is. So remember that in the original problem, we had actually an angular velocity, which caused some acceleration field. But we reformulated that as a body force. And that body force was, in terms of the potential, was minus 1/2 rho omega naught squared. X1 squared plus x2 squared. So those are the most important, let's say, two important functions that eventually deliver us the solution. And the solution comes in the form of, so far, stresses. So we found that the shear stress is equal to 0. And the normal stresses have a rather simple variation. Okay, so here I'm plugging in explicitly the values for the constants A1 through A5 that you have in your notes. Now I'm writing this down because eventually I would like to demonstrate or make a comparison with the numerical solution. Okay. So one final critical piece of information that we employed to derive the solution from this Airy stress function was the following. Well, this is the simplest polynomial Airy stress function that I proposed. And then I went ahead and I used the boundary conditions. The boundary conditions are traction-free boundary conditions at the top and right edges. And eventually, with those boundary conditions, I found out the values of A1 through A5. And then I invoked compatibility, and I found that there was a conflict between the boundary conditions and compatibility. And then that led me to conclude that the Airy stress function, the exact one, can possibly not be polynomial, because I also commented that if you add higher order terms here, really they will identically vanish. So if you want to work with a polynomial one, this is the form of the Airy stress function. So that being the case, if I want to stick to this form, then I have to sacrifice from something. And compatibility is not something I can sacrifice from. So I sacrifice from the boundary conditions. And in particular, I said that instead of pointwise enforcing sigma 11 equals 0 along that edge, I integrated sigma 11, allowed it to be pointwise non-zero. But the integral, I said, should vanish, because in a statically equivalent fashion, the net force on that surface is 0. The moment is also 0. So that's what I enforced. And with that, I got sigma 11. And now if you look and plug in x1 equals a, that means we're on the right edge, this term vanishes, but this term does not, right? So this is the term that violates pointwise boundary conditions on sigma 11 on the right edge. But if you integrate that term, it is 0. And its moment is also 0, because it's a eventually even function. So that was the scenario that we ended up with. So this term came with, or it is the term that violates the sigma 11 boundary condition. And what is also important to remember, that with or without this term, the remaining stress field is not exact unless the Poisson ratio is equal to 0. That's also something we concluded. And in particular, if it is equal to 0, and if you omit that term, you satisfy compatibility, all the boundary conditions, and everything with this Airy stress function, and the resulting stress field is that. Okay? So now that we have this approximate Airy stress function and this approximate stress field, really we need the Airy stress function alone, we're going to go ahead and also calculate the displacements. Okay? But before I do that, let me immediately demonstrate the approximate nature of this solution and how it compares with the exact, or let's say numerical solution. All right. OK, so now what I'd like to demonstrate is the solution on, right? I'm modeling only this part of the spinning beam. And the reason is because everything is symmetric. So I will see the same picture somehow reflected over the symmetry planes, x2 equals 0 and x1 equals 0 axes. Okay, so that's what I have there. So here, these are symmetry planes. And yes, I do have a angular velocity, but eventually I'm going to impose that, as I did in the spinning disk, as a body force, and in fact, as we also did in our analytical formulation. And so what I've done also here is eventually you will see a comparison with the analytical solution. For the analytical solution, I went ahead and entered the expressions for all of these constants, A1 through A5. The parameter plane indicates omega. So a plane will take a value of 1 over 1 plus nu if it is plane stress. So I start with a plane stress setting. It will be 1 minus nu if it is plane strain. So everything is sort of reflecting the parameters of the analytical solution, so that when I vary the parameters, I can immediately compare with the analytical solution to see how well my analytical approximation is doing. Okay, so those are the parameters. Again, I have some angular velocity. Omega naught is the same as in the spinning disk, actually. And the width is 1. The height, the B value, is 0.5. So present the ratio of B to A is 1/2. It's pretty large. So that being large, and since I already discussed that there will be some end effects due to the integral formulation of this boundary, the relaxation of the boundary condition, and that the end effects will be of order somehow B, okay? I expect that the larger the B is, the more the end effects that I introduce due to my approximation will diffuse into my domain. And conversely, the smaller the height is, B is, the better my approximation will be. Okay? And as it becomes smaller, actually, notice that, right, this term will eventually be negligible with respect to this one, because if B is much less than A, the order of magnitude for the largest sigma 11 will be much larger than sigma 22. And that's because if it becomes thinner, I'm going to have plane stress along the x2 direction. Along x3 plane stress or strain, doesn't matter. But along x2, if it's very, very thin, it will be a plane stress setting. Okay? And then I will have a spinning rod, as I commented. Anyway, so now finally, let me first begin with a Poisson ratio of 0. Okay? So I have the parameter here, and I'm going to vary that. All the other parameters are just entered magnitude-wise without the units. So let's now go ahead. So now, if there is no Poisson ratio, of course, I pull, and there is some very, very, let's say, symmetric deformation. So the rectangle remains as a rectangle. And what you see here is the sigma 22 component, okay, of the stress. So let us make this thinner. Okay. Oops, sorry. So this is sigma 22. Okay, and now what you see is, right, so it's nu is equal to 0. Omitting the red rectangle, right, I should have the exact solution, right? So the exact solution proposes that, or suggests that, the sigma 22 is a function of x2 alone. And that's what I see here. There is a variation only along x2, and I don't see a variation along x1. Good. And likewise, if you look at sigma x, okay, you will see a variation along x1, just like my solution suggests. And if you look at sigma 12, it should be 0. And when I write sigma xy here, you will see numerical dust. So the magnitude is 10 to the minus 7. It's essentially 0. Okay? So everything is just spurious, all the numbers you see here. It's extremely small, so we neglect it. Okay, so now everything looks great. And then if you look at if I take a cut, so what I will always do is I will look at the variation of sigma 11, this one, okay, and also the displacement along the one direction, along that line at x2 equals 0 line, okay? It's this line. Okay? So this is the variation of the stresses. And I will always plot with the blue line the numerical solution that comes from the finite element solution in this program. And the analytical solution is my solution. It's that solution. Right? And you see that there's a perfect match. The two lines are virtually on top of each other, and they have to be. They're not only virtually, they are actually on top of each other, exactly. If you look at the displacements, we have not solved for it yet. I will in a few minutes. The displacement match perfectly. Okay? So that also verifies everything that we have done. So in a sense, we're crunching through all these calculations, but it's nice to see that there's a perfect agreement with numerics, or in this case, the numerics agrees perfectly with our analytical results. Okay, so that's good. But I know that already if nu is equal to 0, the solution is exact. I'm not really so much worried about it. So let's see what happens if nu is not equal to 0. So I'm going to go ahead and set nu to my favorite value, 0.3. And I'm going to compute the solution once again. And then I would like to look at the variation first of the stresses. So first of all, when the Poisson ratio is 0.3, what you see is something that it's different than the spinning disk problem. But again, the stresses are higher here. They are less here. The contraction is different here than in the middle region, etc. It's not so exciting, but I showed the deformation anyway, right? Remember that our coordinates align with the rotating structure. So this structure is rotating like this, okay? Not like that. That was a spinning disk setup. So it's rotating in the plane of the curtain. Now, what is more interesting is to look at the stresses. And let me begin actually with sigma xy, okay? Now, this is our solution, approximate solution, irrespective of what the value of what the Poisson ratio is. So now I look at sigma xy, it's not 0, okay? Our solution is approximate. So I am predicting it's 0. In reality, it is not 0. You may want to keep the order of magnitude, if we can, in mind. It's about 10 to the minus 4. Okay? So it's not 0. It's 10 to the minus 4. Let's look at sigma x. Okay? Sigma x, in my solution, in my approximate solution, has both an x1 and an x2 variation. I cannot really judge how good that one is, and for that reason, I'm going to compare the solution eventually along the line. I will show you in a minute. But let's look at the order of magnitude of the solution. It's like 10 to the minus 3 times 5. So it is more than an order of magnitude larger than sigma 1, 2. Okay, than the shear stresses, which I predicted to be 0. So the exact solution says it's not 0, the numerical solution, but I predict it's 0. So now, eventually, what we will observe is as the height becomes much smaller than the width, then they will be much less than the shear stresses will be much less than the normal stresses. Okay, so let's look at also sigma y. Okay, order of magnitude-wise, at this stage, it is similar to sigma 1, 1. Okay. And now, have a look here. This is my prediction. I predict only a variation along the 2 direction, but obviously, variation along only the 2 direction is a picture that works rather well here, but not in this region. Okay? So this is sort of the end effect that really is existing in the actual numerical or exact solution as well. So I introduce an end effect analytically, but in the exact solution, there is actually also an end effect. So there are 2 end effects. I am sort of doing some tricks, right, in the analytical solution so that I'm eventually going to argue this part will eventually be negligible. In my analytical solution, I am also introducing an end effect. I'm going to also neglect that. And in the middle portion, there will be a hopefully very good match. So that's eventually the idea that we are going after. So now, the variation of sigma 1, 1 and also the displacements, perhaps it's not very clear. So for that, let's go and look at the line solution or the value of those quantities along that line. And again, blue is numerical, red is analytical. I mean, OK, of course there's an error. But even at this stage, it is remarkable that we are so close to the exact solution, despite all of the approximations that we make. If you look at the displacements, similarly, in the middle portion, where the variations are very close to the analytical solution, the match is rather good. Away from that, the match is bad. So near the end, we are making some error that appears to be significant at this stage, but still it's not too bad. So now I'm going to go ahead and make the width of the beam 0.1. Okay? So B over A ratio is now going to be 0.1. And it is not very, very small, right? But eventually, what we will see is a couple of things. Now, one, this is the variation of sigma y. And now, as we wanted, as we wished, if I omit this this end portion, which is indeed now of the order of, this is B. So this portion is of the order of B, roughly. And if I omit that portion, variation is almost perfectly in the 2 direction alone. And nothing in the 1 direction can be observed, right? So now we are fitting that form. And if I go ahead and compare the stresses sigma 1, 1 along x1, x2 equals 0, the match is now virtually perfect. It is not perfect. If I zoom in, the lines will deviate from each other, right? They are not the same, but they are extremely close to each other, right? So at this scale, you cannot distinguish the 2 lines. And if you look at the 2 displacements as well, they are virtually overlapping with each other, which demonstrates, again, the idea that as the height decreases, all my expectations hold, and I approach to the exact solution. OK, great. So the last thing perhaps we'd like to emphasize is that our setting, as well as the numerical setting, but in our case, what's important is the analytical one. It doesn't matter whether it's plane stress or strain. We're in a unified setting. So now I will go ahead and pick for my solution not plane stress, but here I will pick plane strain. Now I have to be careful because when it's plane strain, this parameter is supposed to be 1 minus nu. So I will make that 1 minus nu. And let me go compute. And then I will only show you the comparison of sigma 11 and displacement along the line. This is sigma 11, and this here is the displacement, right? Okay. Right? There's again a perfect match. And again, as the analytical solution suggests, sigma 11 is maximum. Always just also realize that. It's maximum in the middle. It vanishes towards the end. And displacement, on the other hand, there is a symmetry plane here. So here I don't expect any displacement, and then it tries to expand. So displacement increases as I move along the x1 direction, and agreement between the two solutions is perfect. So, so that's the idea. So this verifies everything that we have done, and also the analytical solution for the displacement that I will now also derive. Okay. So therefore, let's go ahead with the solution for the displacements. This is the last piece of the puzzle. Now, one reason, of course, why I'm showing you the numerical solution is not only to show you these main features, but also to show that after all this is done, right? I mean, does the solution make sense at all, right? It almost seems sometimes hopeless that what we are obtaining could possibly make sense at all, but it does, okay? All of the underlying assumptions, all of the machinery, all of the assumptions that we are making are really actually very careful steps, okay? So among that, let's say, analytical mess, displacement is one of the, I suppose, the messiest ones. And I've shown you already that the displacement that we will eventually calculate, they are correct. Let me remind you, in the most general setting, when there is a body force as well, the displacements, well, actually, the displacements with or without a body force have that form, okay, where psi is a function that must satisfy 0 Laplacian, and also psi comma 1, 2 is equal to Laplacian of phi, and if there is a body force, there has to be an additional term. Okay? And I've discussed why we introduce such an additional function, and why that function has to satisfy these additional criteria. We've done that 2 lectures ago. Okay. So I know what the Airy stress function is. It's here. So let me first go ahead, and since I know the Airy stress function and the potential for the body force, let me first go ahead and calculate psi comma 1, 2. So psi comma 1, 2 is equal to Laplacian of phi. So it is right, phi comma 1, 1 plus phi comma 2, 2, to remind you. So it's going to be 12 a1 x1 squared plus 12 a3 x2 squared plus 2 a4 plus a5, and then minus the body force, or the potential for the body force. So it's going to be a plus 1 over omega minus 2, 1/2 rho omega naught square, x1 square plus x2 square. So since psi comma 1, 2 is equal to that expression, if I integrate it twice along, well, once along x1 and once along x2, I should be able to get a general form for this function psi. So if I do that, so let's go ahead, once along x1 and once along x2. So it's going to be 4a1 x1 cube x2 plus 4a3 x1 x2 cube plus 2a4 plus a5 x1 x2 plus 1 over omega minus 2, 1 over 6 x2 cube. Okay. Plus so that portion is just the integral of what I already have, but if I take the derivative of what I'm about to obtain with respect to 1 and then 2, I should end up with this. So there is no reason why I should not have some function of x1 alone and another function possibly of x2 alone. Those functions, they might be 0, but in general, I should allow them. OK, so what I've done is I have made use of that. Okay? Now I still have to make use of this portion. So let me go ahead and now enforce the fact that the Laplacian of psi has to be equal to 0. Okay, so we have 0 equals comma 1, 1 plus comma 2, 2, right? So this one has a comma 1, 1. So 24 a1 x1. Well, actually, let's go like this. 24 a1 plus a3 x1 x2. And then these terms. And f double prime plus g double prime. Now, I'd like you to go ahead and verify by yourself at home. This term identically vanishes. Okay? There's nothing I need to do. Okay? We have the values for a1 and a3, the coefficients a1 and a3. They are functions of x1 and x2. So if you go ahead and do that substitution, you will see that that term is equal to 0. So we only have to satisfy f double prime plus g double prime equals 0. This is a function of x1 alone. That's a function of x2 alone. So if I call this a, then this must be equal to minus a. All right. So let's continue over this on this board. Well, actually, we can't squeeze, I guess, the solution in there. So f of x1 is equal to a over 2 x1 squared plus, let's say, bx1 plus some constant and g of x2 is equal to minus a over 2 x2 squared plus cx2 plus some constant. Okay. Now, if you eventually see that f and g go into psi and only derivatives of psi are relevant to my goals, then I see that these constants are not relevant, so I don't care about them. I just cross them over. Hence, we now have the form of the displacements. Okay, so let me record them for your reference. So the general form, so 2 mu u1 is equal to, right, minus phi comma 1 plus omega times psi, okay, comma 2. Okay, I'm going to write down step by step. So the first term I'm writing is minus phi comma 1. Let me directly write down the results because there is nothing really much to highlight here except for the results themselves. So that's minus phi comma 1, and then I have omega psi comma 2. Okay, and psi is the function that we have just derived. I am not making an attempt to simplify this form, unlike for the stresses. So that's mu1, and I'll go ahead and write down mu2 as well. So that's minus phi comma 2, and then plus, similarly, omega psi comma 1 this time. Okay, so that's for your reference, and I've already shown you that that actually is a correct result. Okay. So of course, we have some constants, and you will notice that these are associated with rigid body displacements. And for one component, minus some constant times x2. For two, minus that constant, x1. That somehow has to do with rigid body rotation. Okay, so I need to fix or constrain rigid body rotation and displacement in order to fix the solution itself. And I observe that at x1 equals 0, okay, so I'm going to do some sliding here. So at x1 equals 0, along that line, I do not expect any displacement along the one direction. And similarly, along x2 equals 0, because it's a symmetry plane, I don't expect a displacement in the true direction. So at x1 equals 0, u1 is equal to, right, if you plug in x1, all of these terms identically vanish, except for that one, minus a x2 plus c, and x2 equals 0, 2 mu u2. Again, if you plug in x2 equals 0, all of the terms will identically be 0, except for the rigid body motion part. Okay? And if these are supposed to be equal to 0, for all values of x1 and x2, I know that a B and C have to vanish. Okay? So these terms are actually allowed functionally, but eventually in our solution they're not there. Okay? So the final really displacement field is everything omitting these rigid body motion terms. And that's what I used when I was comparing with the numerical solution. Okay, so that completes our solution of this problem. So now we had the beam, and it was spinning, right? So this was the problem that we were looking at. And now, of course, since I had the beam, I'm going to hold it at one end and I try to bend it. So in other words, I'm going to look at the cantilevered beam problem next. Okay? So again, a plane strain or plane stress, intrinsically 2D problem. It's also a nice problem. It will help us, again, understand how to construct the Airy stress function based on very, very simple observations. Okay? So any questions on this example before I erase the board? Now, let's move on to a new problem, which is the cantilevered beam problem. So we're done with the spinning beam. So now instead of rotating the beam, I'm going to take the beam again. This time, I'm going to fix one end of the beam to a wall. This is the physical setup of the problem. Again, the beam, I'm not really interested in the thickness direction. So now what I'm drawing here is, if you like, the front view. It could be plane stress or strain. And if it is indeed plane stress, then the thickness is, or the dimension along the x3 direction is supposed to be very small compared to the other dimensions. But aside from that, I'm really interested in this picture. Okay? But I'm drawing it nevertheless to show you some dimensions. So the thickness is T. The length of the beam in this case, let's call it L. And the height is h. And I'm going to take this coordinate to be x1. That one is x2. Okay, x2 equals 0 is the middle of the beam. All right, and perhaps I should also draw. This would be x3, and that would be, again, x2. Okay, so x3 is the out of plane direction. Now, that's the setup, and I could now do several things. I could put a distributed load, I could put a force, I could pull on it, I could put a pure bending moment. What I'm going to do is I'm going to put a vertical force. So, of course, now I'm going to comment on it shortly. I don't know, and I don't really care how exactly this force is exerted. There could be some complicated stress distribution on that surface. So it's not necessarily traction-free. It cannot be because there is a net force. But the statically equivalent representation of that force is that there is a, or that stress distribution is that there is a vertical force in that direction. Net moment is equal to 0. Net normal force is equal to 0. Okay? So even if the actual distribution is not a pure shear stress distribution that results in that, even if there is something else, it is statically equivalent to that representation, and all the effects due to a more complex distribution will be an end effect on that surface associated with Saint-Venant's principle. I don't really care what the exact distribution is. So in this problem, the body force is equal to 0. I also do not have acceleration. Because the body force is equal to 0, the potential is also equal to 0. So I don't need to worry about that. It simplifies my procedure a little bit. So again, we're in a generic 2D setting, plane stress or strain. So one thing I'd like to comment on at this point is the ratios T over H and H over L are important. Okay. So this is something eventually that you will remember, and perhaps you should remember from ME 231, because this is a problem that was, this is a fundamental problem that we analyzed in 231, banding problems, banding stresses. And for instance, the thickness dimension is important really because in general, if it's not plane stress or plane strain, an ideal setting, there will be variations along the thickness direction. But our approach in an intrinsically 2D setting assumes only ideal plane stress or strain. And in those cases, the thickness dimension, the X3 dimension is not important. If those are not ideally satisfied, this ratio is important. And H over L ratio is, of course, also important because there will always be end effects, either due to the way these forces are applied or because of the fact that there's a constraint on the right-hand side. If it is very, very short, these end effects will start to dominate and affect the quality of our analytical solution, just as they did in ME 231. Okay. But having said that, let's move on with the most important observations. And those are the boundary conditions. Now, the boundary conditions come in two forms. On the left edge, x1 equals 0 surface, I have boundary conditions that are associated with stresses. At x1 equals L on that surface, I have boundary conditions associated with displacements, right? Because this is a fixed constraint on that surface of the body. Let's begin with the stresses first. And I have two types of stress boundary conditions. One pointwise, and they say that on the top and bottom surfaces, I have traction-free conditions. Traction-free, so stress on that surface, sigma 2, 1 and sigma 2, 2, they should be 0, both on and on that surface. So plus minus h over 2, sigma 1, 1 and sigma 2, 2 should vanish. That's my only pointwise boundary condition on stress. So now I go to an integral formulation of the stress boundary conditions on the left surface. And there, as I mentioned, I'm going to enforce static equivalence. Okay? Again, in view of the Saint-Venant's principle, and which we have observed over and over again numerically, I don't really care about the exact distribution so much, at least. All I want is that when I integrate sigma 1, 1 on that surface, I should not observe a normal force. So that is the first condition. And the second one is when I take the moment of the normal stress distribution, sigma 1, 1 times x2, so that's the moment arm. Again, that should be equal to 0, 0 net moment. And finally, something that does not vanish, if I integrate sigma 1, 2 on the left surface. So just look here for a second. So I'm on the left surface. So the positive direction on the left surface, sigma 1, 2, it points downward. So if I integrate sigma 1, 2, I should get plus p and not minus p. And I'm integrating only along dx2, right? Newton per meter squared, Newton per meter. So this is p over t. T is the thickness dimension. So in other words, this integral really represents the average shear stress along a line that I take, okay, if you like. If it's plane strain, it's not a problem. But if it's plane stress and t is not that small, there might be variations in sigma 1, 2 along the green line. But if I average it, I should be pretty close to the value of sigma 1, 2 point-wise. Okay, so sigma 1, 2 is really average stress along that green line. Okay. In an ideal plane stress setting, it is what we are computing. It is supposed to be, let's say, exact within the limits of our approximation. So those are the boundary conditions on stress. Okay. And we can also, so ... means physical boundary conditions on displacement. Let's also formulate that. It is nothing but vanishing displacements at x1 equals L. Now, just for a second, I'd like to sketch something. Don't write this. Actually, I will sketch two things. The first one is that in the spinning beam problem, if I had enforced pointwise sigma 1, 1 vanishing along that edge, right? This was x1, and that one was x2. I had rotation, omega naught. Then I had a clash with compatibility. I called sigma 1, 1 pointwise vanishing on that edge a physical boundary conditions. That's what I observed from the physics of the problem. And then I relaxed it and called that an integral formulation. So in this case, we already have an integral formulation. I am already calling it physical because of the fact that here the situation is different. I am physically really, due to Semmelweis principle, not concerned with the particular way the stress is distributed. I'm just interested in the statically equivalent representation. So it's physical for me. So now eventually the physical condition on displacement on the right edge is that at every point it should be 0 because it is fixed. It cannot move. It's stuck to the surface. It cannot contract. It cannot move outside. So that's clear. But it turns out eventually that our analytical solution will not be able to pointwise satisfy this condition. Okay? So when the time comes, I'm not going to be able to enforce the physical constraints on displacement at x1 equals L, but I will make an error, but that error will be an edge effect that is limited to a very thin region, and therefore, again, I will not worry about it so much. So this one, when the time comes, I will relax it. I will relax it. So let me note here that this is to be relaxed. Okay, so that's the first remark I'd like to make. The second remark I would like to make is concerning the setup of the problem. Now, you might wonder, well, eventually I have the beam and I'm putting a vertical force, right? What if I did something else? What if, for instance, I put a pure bending moment or I put a tensile force. Let's call that N, and that's a pure bending moment, M. Now, it turns out that the solution steps are almost identical. So I will solve this problem, and if you want to think about this problem, in fact, I encourage you to think about it, and I can discuss it with you. You will see that you can follow the same steps and obtain the solution to this problem as well. Okay? So I'm going to solve this one because, in fact, this problem is slightly, just slightly a little bit more complicated than this one. And eventually, what if I have a problem where I have all of these forces? Well, I solved that problem. That's the red problem. You can go ahead and solve the black problem. And if you want the solution to this problem, you use superposition. Okay? So it's pretty straightforward. All right, so those being the comments, I'm going to go ahead and erase these. And I'm going to continue with the solution. And the first important step in our solution is the construction of the Airy stress function. And remember, what I would like to have is, I I have an Airy stress function. Its existence ensures that equilibrium is satisfied a priori. It gives me the stress field. I need to enforce compatibility on it to specify or really restrict the form of that Airy stress function. But first, I need to construct a problem-tailored form of the Airy stress function because it will simplify my life a lot. And in the spinning beam problem, I did that with two very simple observations. Again, here, it's going to be rather two simple observations that will help me construct the Airy stress function. So those observations are the following. I'd like to highlight the keyword. Always, we want to simplify our life. Right? So the observations are the following. The first observation is that I'm going to have, when I take a cut along any position along the length of the beam, right, I will observe a certain stress distribution. Okay. So again, don't write for a second. Let's look at these two observations together. The first one is, right, there is a force. And if I take a cut at any point along the length of the beam, we know from ME231 that there is going to be a moment exerted on that cross-section, right? Not only a moment, but also a transverse shear force, right? And we used to call that V and M, okay? But in any case, well, the moment will induce normal stresses, sigma 1,1. And the presence of the shear force at any cross-section will induce shear stresses, sigma 1,2. Okay. Now I'm looking at only 1,1, and 1,2 will remarkably come out of the same observations. So 1,1, I expect that here, first of all, statically equivalence representation of sigma 1,1, it's this. One particular scenario is sigma 1,1 is actually point y0 at every point. But as I move along the length, the moment here at this point is 0, so no wonder sigma 1,1 could be 0. It doesn't have to be, but it could be 0. As I move along the length, however, the bending moment due to this force will keep increasing, which will induce sigma 1,1. And the further I am from the edge of application of the force, the larger the moment will be, and the larger sigma 1,1 will be. Does that make sense? Okay. So that's a very simple observation. Sigma 1,1 is proportional to the bending moment. I'm going to call it N. Of course, we are talking about the bending moment about the x3 axis, but I'm not going to write that explicitly. So M is the bending moment, and M is proportional to x1. And this is something that I am concluding from statics, really. You know, it's statics plus a little bit of course, mechanics of materials. Okay. So this part from mechanics of materials, and that one is really from statics. So we don't really need to know elasticity to conclude that. Okay, the second observation is a very simple observation. Sigma 1,1, as I move along the height of the beam at any given location, x1, it's not necessarily a constant. It will vary. And in fact, I remember from 231 that there's a neutral axis concept, for instance, this axis. And if I go up in this setting, above will be tension, bottom will be compression, but whatever. But really, in this case, all I need to realize is that sigma 1,1 is not necessarily a constant, and I'm going to write that. Okay? I don't know how it varies, but that's something that I will find out. So I'm just writing that sigma 1,1 is for sure proportional to some function of x2 at fixed x1. Now, this is something that you're going to see now shortly with a view towards what we're about to do. I'm not going to say that sigma 1,1 is proportional to some function f, and in fact it is, but instead of using f, I'm going to introduce a function, eta, such that when I take its derivative twice with respect to x2, I get this function f that I'm trying to find out. Okay? And you will see why I did this. It simplifies my integrals at some point. Okay? So for convenience, we have introduced a function eta. So therefore, we expect that sigma 1, it is a function of both x1 and x2. Okay? Now, perhaps here is the most important trick. What we are doing is sigma 1, we are saying it's proportional to x1. So I'll go ahead and write x1. And it is proportional also to some function of x2. And instead of writing f, I'm going to write eta double prime x2. Okay? And now I am proposing this form. So this is our expectation, and these are our simple observations. Now, when you look at the left-hand side, there's a function of x1 and x2. It's not, in general, necessarily that such a function be represented as a function of x1 alone and then a function of x2 alone. This is almost like the separation of variables approach that we once used at the beginning of the semester. So this is a very actually particular proposal. So it might raise eyebrows. Is this valid? But these are the observations that validate sort of this type of approach in our case. It's based on our experience. So we have some understanding of the problem, and this is what we are proposing, okay, based on those two very simple observations. And now, remarkably, this is the core statement of our solution. Do we understand this part? Okay, so they're reasonable assumptions. We'll see if it works out. So the first thing we are going to do now is we are going to recall that sigma 1 is the Airy stress function, comma 2. Okay? So I'm going to go ahead and integrate towards phi. So phi is equal to integrating this twice with respect to x2. So now you see why I introduce a new function eta, which has a double prime instead of f. Because when I integrate twice with respect to 2, I'm going to have now simply eta. And that's the function really that I'm interested in. Okay, x1, eta of x2. And I am integrating twice with respect to 2. So I could have the following setup. So first of all, I could have a function. So these are extra. Right? Let's write that in blue as we did in the last problem. So I can have some extras here that vanish when I take two derivatives with respect to x2. And I could have a linear function of x2 multiplying some function of x1. So I am sorry that I'm using now all the Greek alphabet. Right? This is xi. Okay? And now, right, if I take the derivative of this with respect to x2 twice, one derivative, second derivative, it dies away. And now I could also have a pure function of x1. And I'm going to call that zeta. And I'm probably picking these up because of the reference that I borrowed this example from. So this is the general representation of the Airy stress function. OK. And usually when I have a function that depends on only one coordinate, I really drop that representation. But in this case, I will have something that's a function of x2, another thing a function of x1, plus they're in Greek alphabet. So I'm going to try to explicitly indicate the dependence of the functions, whether they are on x1 or x2. All right. So based on these, I can calculate not only sigma 1, right? So now if I take two derivatives with respect to 2, that's sigma 1. But I can calculate also sigma 2, which is phi, comma 1. Okay? Two derivatives with respect to 1 vanishes. These two stay. So it is x2 xi double prime x1 plus zeta double prime x1. And sigma 1, 2 is minus phi comma 1, 2. So one with respect to 1 and another with respect to 2. This one dies away. These two survive. So it's minus eta x2 and then minus xi prime of x1. All right, so now we have the Airy stress function form. That's the form. And we also have the stresses, sigma 1, 1, sigma 1, 2, and sigma 2, 2. So now I have done my basic observations to have a problem-tailored form for the Airy stress function. And now what I'm left with is two sets of things. One, the boundary conditions, and two, compatibility. Now, those I need to make use of in some clever order so that I have the fastest route to the solution. So here, there is really no one single approach. You can immediately go and enforce compatibility on phi, or you can try to make use of the boundary conditions. I'm going to follow a route that will lead us as fast as possible to the solution, which means before compatibility, in fact, as we did last time, and that's often the case, it's good to make use of some boundary conditions at this stage. And I want to make use of the physical boundary conditions. And not all of them, only one of them at this stage. And in fact, I'm going to go ahead and make use of the traction-free boundary condition on the top and bottom surfaces. So let's make partial use at this stage. OK, so sigma 2, 2, because top and bottom surfaces are, or edges are traction-free, at x2 plus or minus h2 for any value of x1, I need to have 0 stresses. So at the top surface, so now this is sigma 2, 2. I'm making use of this boundary condition because I have an x2 here, essentially. So I'm going to plug in either plus or minus h2. So at the top surface, plus h over 2, c double prime x1 plus zeta double prime x1. That should be equal to 0. And at the bottom edge, minus h over 2, c double prime x1 plus zeta double prime x1 should be equal to 0. My x's in particular will rapidly deteriorate towards the end of this example, but so far I'm paying a lot of attention trying to make it look neat and different from zeta. OK, so those are the two boundary conditions. I've only made use of, OK, I hate doing this, but I'm doing it. I'm only making use of this so far. I have many more things to make use of, only sigma 2, 2. Right, so if I sum these up, these vanish. So I see that zeta double prime has to be equal to 0. And if zeta double prime is equal to 0, xi double prime is also equal to 0. Hence, right, so first of all, right, if xi double prime and zeta double prime are both 0, sigma 2, 2 is equal to 0. Okay? And actually, that's something I can relate to from the setup of our problem from our 231 Basic Mechanics of Materials course, that in this problem, I do not really expect any stresses to form in the vertical direction. I'm not squeezing this or doing anything else, so that should vanish. So sigma 2, 2 should be equal to 0. And I need the functions xi and zeta, I know that they are going to be necessarily linear functions of x1. So let me call these linear functions ax1 plus f plus gx1 plus h. Okay, so what I'd like to do is, before finishing up this, at least lecture, is pretty much obtain the form of the Airy stress function. So we have a little bit more to go. So now at this stage, of course, you might also be curious what happened to B, C, etc. I'm just picking these constants for some reason, maybe again, based on the reference book I'm using. A, F, G, H, eventually B, C, D, everything will appear. So I made use of one strong or pointwise boundary condition. Now, before making use of anything else, now I'd like to immediately go to compatibility. Because if you now look at my Airy stress function, yes, I don't know what eta is possibly like, but I already found out what xi and zeta are. And it turns out that if I now enforce compatibility, I will be able to also find out what eta is. And with that, I will know what the Airy stress function is. And that's a very good start for further proceeding with the solution. So let's do that over here. Again, there is no particular order here. This is just based on experience of the people who have solved this problem. Okay? I'm trying to take you through the fastest route to the solution. So at this stage, we have phi is equal to x1 eta, x1 eta of x2 plus x2 xi of x1. Xi of x1 is a x1 plus f plus zeta, gx1 plus h. And it must satisfy the compatibility requirement, which says that phi comma 1, 1, 1, 4 derivatives plus 2, phi comma 1, 1, 2, 2 plus phi comma 2, 2, 2 should be equal to 0. And the function is rather straightforward. 4 derivatives with respect to 1, that is equal to 0. If you take 2 derivatives with respect to 1, 2 derivatives with respect to 2, every term drops. So that is also equal to 0. And 4 derivatives with respect to 1 delivers x1 eta. So Roman numeral 4 indicating that I'm taking 2 derivatives of eta, which is a function of x2, which therefore must be equal to 0. Okay. And therefore, eta, 4 derivatives x2, must be equal to 0, which suggests that eta is a cubic function at most of x2. Okay. And I picked some coefficients to represent that polynomial. Okay, so we are really done with the bulk of the solution. So what I will do next time is, since now I know exactly what actually the Airy stress function is, right? So I can slide up this board. I have just found out what eta is. Xi and zeta I've already found out. I know really what the Airy stress function is. So I know exactly what the stresses are in problem-tailored form. But now I need to restrain those further by making use of all the boundary conditions that I have not yet made use of. Okay? So that's essentially what we're going to do next time. All right? So I'll see you then.